Hello, everyone. Welcome and happy New Year to everybody here. We've got a couple of familiar faces with us today. Ritesh, Shanay, Happy New Year.
Hi,
Happy
Ahmed.
New Year.
It almost feels like a long time ago that we were celebrating the New Year. To be honest, we've done a lot of testing in the last couple of weeks, and I think we're going to talk about a lot of it today. It's about just the newest learnings we have around fine-tuning the LLMs that we're working on right now. This is an example of a use case that we've been post-training around. It has to do with negotiation, which is obviously a skill that's pretty handy in the business context. But what makes it really interesting is the fact that it's not a very verifiable task. And so it makes for a very fascinating use case for us to post-train, fine-tune, and learn. And then we can share those learnings with the rest of you. So welcome to both of you. Where do you want to start? Shanay, I know you've been doing some tests, and of course we had fine-tuned a model that we quite like the results around. And then what we started to do was iteratively create newer and newer versions, just so we could start to understand what a good cadence looks like, and of course, what type of improvements we could see by playing with a few different parameters, starting with the training data, the base model itself, capacity to learn, reasoning, and many other things, obviously the size of the base model as well. So where do we want to start? I think folks would love to hear what that journey looked like for us.
Yeah. So when we first started fine-tuning, so our fine-tuning are all distillations. We use bigger frontier models to create the data set and then train smaller models on them, on those data sets. When we started the fine-tunings, we Gemini 2.5 Pro was the frontier model at that point, and we used that to create our data set. So it was the teacher model, and we created the data set using that, and we fine-tuned on top of that. The results of those fine-tuning runs were good enough. Essentially, they were good so that they were good for a version 1, which we can release to a beta, or allow people to try it out without getting embarrassed. So that was one thing that we got from those fine-tuning runs. It was able to mimic Gemini 2.5 Pro, but it was not the perfect model. It had mistakes. However, Gemini 2.5 Pro also made those mistakes. So essentially, in those fine-tuning runs, our goal was not very high. Our goal was low, and the fine-tuned model was able to meet that low goal. Post that,
Sorry, I'll play that back. Said in another way, what you wanted to do was have a much smaller model mimic the type of quality of experience that you were seeing from what you thought was the premier model at the time, which was Gemini 2.5. So your entire goal here was to actually get the same type of experience, quality of experience for the user that they would get if we use Gemini 2.5, but with a much smaller model, easier to serve, faster response times, and what have you.
yes, that is correct.
So classic distillation, meaning, in other words, like, hey, let's get good, let's find an extra size, small model to deploy, execute, run for inferencing, and try to gain most of the upside of the larger premier model. And so we were able to achieve that, but we didn't necessarily think that it was the absolute best quality of commentary. And so we continued with the post training to say, you know what, let's now get to something even better.
Yes, we did that, and I'll walk you through that. So when we started with the second sets of fine tuning to kind of release the V2, we by the time we had Gemini 3 Pro and Sonnet 4.5, both of which are a big improvement over Gemini 2.5 Pro. So we created a new data set, this time using Sonnet 4.5 and Gemini 3 Pro. The data set was much better. Our expectations this time were much higher, because we saw the foundational models were able to achieve a much higher capability. However, when we fine-tuned the same base model on top of that data set, we weren't able to replicate that performance, and we weren't able to get to a satisfactory result.
Got it. So let me now that we're talking about it, you mentioned maybe we can share our screens and take a look at some of these base models and how they compare, because you said something quite interesting. What you said is, since that V1 in which you were effectively comparing your post-trained model with Gemini 2.5 and you were able to see comparable performance, at least based on an expert's perspective, now we had seen much better models out there. So things that were much better than 2.5. So can you show us on a screen, maybe based on artificial analysis scores or something else, just how much better maybe some of these newer models are? And then we can maybe talk about what that means to a post-training use case.
Yeah, just a second.
Okay, so while you're pulling that up, and I think when you mentioned teacher model, this is really interesting, and it's obviously important for everybody who's listening, is the fact that one of the key aspects of fine-tuning is to have a data set that you can train on, right? And also calculate val loss on. And that training data set, that's not something that a human is actually going and creating. Now, a human may actually start to seed information, but at some point, at least in our use case, we're starting to use sophisticated models to take information and create more and more training data set information. And so that's being produced using frontier models. So to begin with, we were using, I guess you said Gemini 2.5 as the teacher as well, or was there something different?
No, yeah, we were using Gemini 2.5 as the teacher to begin with.
So basically, Gemini 2.5 was the teacher, and it was sort of the negotiation agent model for inferencing that we wanted to use as the representative threshold, and we were able to get similar results to Gemini 2.5. So now, where is Gemini 2.5 in this bar chart?
Yes, so Gemini 2.5 is way over here. On the left are all the models that came after it and perform much better than it.
And can you zoom in a little just so we can see?
Sure, one second.
There it is. Okay, just a little more. Okay, so I see that's a 34. Is that correct?
Yes, it's a 34.
Okay, so you got a 34 score on the intelligent index. And so if you look at some of the modern, I guess, which are the ones that you'd want us to fixate on?
Yeah, we can look at the ones which we used. We can look at Gemini 3 Pro and Sonnet 4.5. So Sonnet 4.5 is here with 42 and Gemini 3 Pro is here with 48.
Amazing. So a 48 score compared to a 34, yeah, it's a significant improvement, like 40%. So we see that and we say, okay, this is a much more sophisticated model. And then we kind of come up with two different action items. One is to say, let's use this more sophisticated model to come up with our training data set. That's number one. And then what we say is, let's now also make this the bar, or let's just see how this model performs if we were using it for inferencing, and now try to figure out if we can come up with a model that's been post-trained by us that can actually not just match the expectations we have based on our Gemini 2.5 experience, but let's see if we can actually exceed or meet the quality of experience we get using Gemini 3, for example. And here is where we fell short, because now you are not able to create a distilled model that was able to get the same type of scores on our side based on our barometer for performance. We weren't able to match it. Although it is still the new model that we came up with was still better than Gemini 2.5. Is that correct?
Yes, it was still better than Gemini 2.5.
Okay, so it's better. So basically, we used a more sophisticated training data set to train a model, and the base model the first time around was the same as the base model we used last time.
Yes, we the initial experiments we used the same base model, but then since we hit a roadblock with that base model, we moved on to other base models.
Got it. So at least to begin with, just to keep apples to apples, we said more sophisticated training data set. Let's run it on the same base model and see if we can meet the expectations we have. And we weren't able to, because Gemini 3 Pro had just that much better performance. And even though we came up with something that's better than what we had before, compared to Gemini 2.5, it wasn't able to hit 3. And so next steps were taken. So walk me through what those next steps were.
Sure. So next steps were that, we first moved reasoning. We first moved the base models. So initially we were only trying with one base model. Now we moved to more of them. We started looking at Qwen 3 models that is the Qwen 332B models. Again, we started training it on the data set. We varied a lot of hyperparameters in terms of number of epochs, your batch size, learning rate, LoRa rank, and all those things. So we varied all those hyperparameters and evaluated the model on that. But again, none of the fine-tuned models was able to match the performance of the dataset, that is Gemini 3 Pro.
When you tried different base models, you're talking about different base models coming from different labs, of course, but
Yes.
about the same size. So you're not varying size yet.
No, not yet.
Okay, so basically what we're saying is before we go to smaller or larger models, what we're saying is let's just start with a different base model, roughly the same size, and let's just see if some models are able to give us significantly better results, or at least get to the expectations we have, and they weren't able to. So just quickly swapping out base models to different models was not the ticket to a better experience. Where do we go from there?
Yes. So the next steps are, of course, to you either increase the size of the model and you get to a bigger base model so that you have more parameters. The model is inherently better in terms of logic, etc., because logic is a very important thing when it comes to negotiations. And second thing is that until now, all of our base models, all of our fine-tuning runs were non-reasoning. So the model is trained to directly answer without having any reasoning traces. But now we since we are facing these problems in terms of logic and the model not being able to output a very good response, we need to also start looking at training with reasoning so that we can achieve that better performance.
So those are two different ideas. We'll take them one at a time. So Ritesh, I'll pull you into this conversation. The idea that we would a larger model, training a larger model would get us better results. That would have held true even before we got to the newer training data set, right? So even in the old training data set, had we started with a larger model, we probably would have gotten to a distilled model that had better performance, right? The only difference is we would have had slower inference times. And so what we effectively did was start with a smaller model and just set the bar lower to say, at least, get to the experience quality that we have with Gemini 2.5. But had we stuck with the Gemini 2.5 training data set and actually trained a larger model, would you agree that we would have seen an even better performing post-trained model?
Yeah, I mean, we actually started with an even smaller model. Like we started with Llama 8B and Qwen 2.57B. We wanted models around that size or less than 10B size to be working good. But what we see is that learning wasn't much. That is, they weren't able to perform. So we scaled the model size until it's good enough. And just a recap on our data set, it's not complete distillation. Like we do rejection sampling. Essentially, we take traces of Gemini 3. Or Gemini 2.5 Pro, and we remove what traces that we think are bad. So that's our secret sauce evaluator. So during our evaluation, what we have seen is the models around 32B size or GPT 4.1 mini, which we don't know the size for, are actually doing as good as Gemini 2.5 Pro. When I say as good as is, let's say if Gemini 2.5 Pro gets it wrong, again, the definition of wrong is subjective. However, let's go with it. Gets it wrong maybe 4 out of 10 times. These models were only getting it wrong 3 out of 10 times. So that way we were actually improving upon parent model. So since we have already seen this with the small size or 32B or GPT 4.1 mini, we thought maybe scaling the model size here wouldn't give us the best yield yet. Maybe we might have gone to a model that gets it right 8 out of 10 or gets it wrong 2 out of 10. But we felt that those yields were incremental.
Got it. So even in your previous way, where you started off with rather small models and you kind of got up to 32B, and you were able to you thought kind of get to a sweet spot, and where you felt like even if you had gone to 120B parameter model, you would have maybe gotten slightly better. But now with this more improved, I guess with the more sophisticated training data set, you feel like that 32B sweet spot is no longer the sweet spot. Perhaps the sweet spot is a little higher.
Yeah, that's exactly true.
Now, what is different about this training data set? Because what you're effectively saying is that you feel like, before we go into any other parameter, let's just start with the size of the model. You felt like size of the model, you were capturing most of the upside at 32B with the older data set. Now you create a new data set characterized by the fact that it was created by a more sophisticated teacher model. What is it about this new data set that now tells you that you might need a larger model to capture the goodness of this training data set?
Yes, I think, or if I were to put it in one word, it's actually the nuance that the model is able to get in a scenario is what has improved. Essentially, to recap, how does our data set look like? We start these models with a scenario. The scenario likely a user is on, and then the model navigates the situation with you. It navigates by asking you the right questions, and then after some time, or after 8 to 12 turns, the model gives a preliminary advice, and then the user asks follow-up questions. So this is the structure of the data set. And then with improving the base model, obviously we didn't just swap the base model and get a new data set. We have iterated a lot on prompts. Shanay here has done a lot on that. And also we have added more evaluators as well. That's how we actually got a good nuanced data set. Shanay, do you want to add something on the complexity side?
Yes. So on the complexity side, I'll add it in a different perspective, which is that our evaluators changed quite a bit when we moved from using Gemini 2.5 Pro to using Gemini 3 Pro. As in Gemini 2.5 Pro, we used to have evaluators that looked for very common logic problems, which are very easy to catch. However, when we moved to Gemini 3 Pro, these logic problems kind of just went away. And so we did not have those easy evaluators because we didn't need them. However, we had more nuanced evaluators which were looking for better things in negotiations. They were harder to catch. And so, yeah, that was the increase in complexity.
Yeah. And I think, for everybody out there that's doing fine tuning, look, this is a game that doesn't end quickly, right? I mean, as frontier models get better and their ability to manage logic and score well on these intelligence benchmarks, as they get better, we have to do work to actually harness their power in terms of our own post-training pipeline, right? So the generation of the data set itself, the creation of evaluators as part of the fine-tuning process, but also the expectations of how good it's expected to be. As the market expects something better, where you not only have to train with better data, you have to evaluate it and actually produce better results. So let me ask you this: when you are actually doing the fine-tuning, when you're actually looking at the val loss functions and you're actually looking at the incremental gains from epoch to epoch, are you able to actually see that the performance or the learning is not going as well as perhaps it was going earlier when you had the more simplistic training data set? Is there something without necessarily bringing a human or expert in the loop to actually see what the results look like during the training process itself? Was there any signal that you got from any of the benchmark dashboards that you look at that indicated to you that, hey, the learning rate doesn't seem right?
Yes. Yes, we had we were able to use training loss to distinguish and tell that the training run is not going good. So if we were to compare the training run on the Gemini 2.5 Pro dataset with the one on the latest dataset, we could clearly see that the training loss was higher for the newer dataset, which meant that the model is not distilling properly and is not able to learn as good.
Got it. And let me ask the same question: when you were flipping or swapping out the base models without necessarily changing the size, just to see if a different base model could get you better results. Did the same hold true there, where you saw that the other base models were also not exhibiting improved behavior in terms of the training loss?
Yes, that is correct. The other base
Okay.
models were not also.
Got it. So basically, that's a quick and dirty way of just seeing if whatever your hypothesis is, if it's actually going to give you some promising results or not, without necessarily going all the way and producing a result and then putting it in the hands of some human that has to then go do an evaluation separately. Is that fair?
Yes, yeah, to a certain, like, if the training loss is within an acceptable range, we would like a human to evaluate it. But if it's like very high, then we will want to skip that training run. Yes.
Yeah, and I asked that because there's so many different permutations here. You certainly don't want to have every permutation end with a human, eval, right? So that's
Yes.
going to be important. So you tried a few different things, and then of course, eventually you got to the point where you said, you know what, I'm just going to try a base model that's much higher, much larger. And then of course, so how did that go? Like as you started to test with that, what kind of findings did you have?
Yes, so GPT OSS 120B is one of the big base models that we have been trying it out. We are still midway in our experiments, but we do see that the training loss is essentially lower than what we had in the previous runs using Qwen 3 32B models. So yeah, but we are still not done with the experiments there. So yeah, can't give you the final results right now.
Okay, that's quite a cliffhanger. And then on the reasoning side, have you started any testing there? Because what you're effectively saying is perhaps smaller models can actually pick up some of this nuance, but you have to bring reasoning into the fold, whereas earlier we weren't using reasoning at all. So tell me where you are with that.
Yes. So reasoning experiments, we haven't started with them yet. There is a reason for that, which is that we would like to avoid reasoning if possible, because reasoning increases your time to first token and it makes the latency higher. So we, as I mentioned, we are running bigger models first. So if we are able to get to the good point using the bigger models itself, we would want to use them instead of running them with reasoning to save on latency there. So if the current experiments they succeed, then we stop. Otherwise, we go to the experiments where we start including reasoning.
And let me ask you this, Ritesh, like, just given the nature of this task, we made the conscious decision of training without reasoning, so non-reasoning model. Why is that? I mean, other than the fact that we obviously wanted to use fewer tokens, hence have better time to first token, which performance always matters. Was there a reason why we felt like non-reasoning model could actually compete favorably, or did we always know that the reasoning variation would be better, but it's just that for V1, we had gotten to the sort of threshold of satisfactory performance, and hence we just kind of paused it and figured we'd introduce reasoning in a later stage if necessary?
Our hypothesis has been that in this particular negotiation advisory case, non-reasoning models should be as competent as reasoning models. The reason being, the performance, I think it depends upon task type a lot. If the task is more, or if the task is more exploratory during test time, I'll elaborate on that. Let's take a task of solving math problems. Like we have all the questions in the world, or we have a training data set of solving math problems. And during test time, or when you're testing the model, the math problems that the model sees are actually not from training data set. They're a little bit of trickery or innovation or adaptive compute is required. Adaptive compute is producing more tokens before giving the answer. So in such cases, reasoning definitely helps because you are doing exploration during test time. However, if your task is simple, or if your task is structured in a way that you can actually get a really good training data set distribution, that is more likely close to your test time, then in that case, reasoning is not required. So we actually spent a lot of time devising scenarios. Scenarios are essentially possible user questions or possible negotiation situations a client could be in. And we took a really good distribution of those in our training data set. So this is why we started with the assumption we probably don't require reasoning here because we have almost all or all possible scenarios given in our data set.
Got it.
Majority of them. Yeah.
So, I mean, effectively, the idea is, and so just to takeaways, quick recap since we're 25 minutes in. Number one is the size of the base model matters. And, for different use cases, for different training data sets, for different levels of sophistication in terms of what you're actually trying to teach, you may have to discover what the sweet spot is. And for more subtle use cases, the sweet spot might be a smaller model because the learning is possible. And for more sophisticated use cases where you're trying to learn something that's a little more nuanced, you probably have to go a little larger to get to the sweet spot. And so as our learnings are getting more sophisticated, we're having to go up to a larger model. And we don't know what that sweet spot is, but we assume that it's larger than the current model that we're using. Number two is, if possible, if at all possible, and you can actually learn the art of reasoning for your craft, for your use case, then that's obviously going to allow you to fine tune a non-reasoning model and get that type of experience that you're looking for without necessarily needing the reasoning exploit capabilities. And the reason to avoid it would be strictly fewer tokens used, less time spent. And of course, if you're not able to avoid it and you're still looking to get better results in a task that requires some level of logic, reasoning, exploration, and search, then probably it behooves you to test out a reasoning model, and you'll most likely see a difference in results. Now, are these things additive, Ritesh? If I were to go larger model and start to introduce reasoning, do you believe that those two things are going to continue to sort of add to the performance, or do you think that at some point a large enough model does not benefit as much from incorporating reasoning? Or do you think that it's strictly going to be additive and it only gets better as you get to larger models?
I don't have an exactly good answer here because it really depends upon the task type. However, it could be possible that it is additive because here Shanay is sharing in artificial analysis. We do see that when or at least for the bigger models, the gap between non-reasoning and reasoning variance is a lot. Obviously, it's a accumulation of overall the benchmarks. So it could be that, but however, it could also be that for negotiation advisory scenario, seeing it good enough traces without reasoning is actually good enough for the model to be to learn the core art of negotiation, where we have things like situation analysis and then looking for alternatives and so on.
Yeah, and that's really fascinating. I'm surprised there's not more research literature on this topic of sort of building reasoning into for the purposes of training and fine tuning. So I'm keen to see what the research says. Maybe we can discuss it later, or if it doesn't exist, then maybe this is an opportunity for us to publish a paper on this matter, right? For tasks that are not strictly verifiable, post-training capabilities that are built on top of increasing size, non-reasoning and reasoning models, or what is the delta in performance based on either some kind of critic model or some kind of human skill scoring would be a really interesting subject, I think, because this is not unlike many other use cases. Certainly, I would say. What do you think?
Yeah, definitely. And in real world, a lot of use cases are actually non-verifiable. Like we know that coding and everything are actually verifiable because you can validate the solution. But when you have agents running in enterprise, especially, more often than not, the percentage of non-verifiable use case is actually more.
Yeah, I think this concept of bundling, whether it's strictly additive and if the improvement as a ratio is consistent, or if it's divergent in either direction, I think is a really interesting question for us to have an answer on. Maybe next time we'll talk about it. And the last thing I do want to discuss, and I know we're getting close to the 30 minutes here. Appreciate everybody joining us. By the way, you can reach us on Discord as well. We talk about this stuff there as well. I want to ask you, we've talked about reasoning, incorporating reasoning. We've talked about the size. We've talked about different base models and how these things have impacted the kind of performance we've seen from our fine-tuned models. Last thing I want to say is the training data set, because the entire conversation started with us coming up with a much better training data set, which led us in all of these different paths. But have we thought about how improving the data set or tuning the data set could actually get us to better learning? Or do we feel like it's important to concentrate on getting the absolute best data set and then figuring out the rest of it separately? Like, how do we think about it? Could there be something we do with the data set, either increase the size of the data set or maybe change the qualities of the data set so that the training loss is more favorable?
Yes. So I can try to answer that. So yeah, you mentioned 2 points. One is the size of the data set, and second is the quality. So as Ritesh mentioned, for quality, we don't just take the data set directly from the frontier models and pass it to the smaller ones. We do have a step of rejection where we filter out the bad generations. We have our internal evaluators which filter out the bad generations. This helps us in improving the quality of the data set and removing the undesirable part. And secondly, as for data set size, yes, of course, data set size matters a lot. So for the experiment where we had Gemini 3 give the data set, we tried 4 different sizes of data, like incremental, and we were able to clearly see an increase in performance as the data set size increases. However, there is one aspect which is the logic that the model has, inherent logic, not specific to negotiations, but just the logic and the way in which the model just uses the language and phrases some sentences, which was a weak point throughout all of these training runs. So essentially, the the benchmark that we were trying to improve, which is negotiations, was improving with dataset size. However, this benchmark, that is logic and like phrasing, etc., was constant as dataset size increases, which also makes sense because we were not trying to improve that, but that is a weak point and a pain point for us.
Got it. So there's certain criteria that seem to be, not disconnected to the size of the data set, but the data set in general was able to impact overall satisfaction of, in terms of the scoring that we did. And is this fair to say that we haven't quite found the sweet spot for our training data set size and it might get larger in the future?
Yes.
Okay, fair. And certainly we know that it's not going to get smaller because going smaller does impact our satisfaction scores.
Yes.
Got it. Okay, sounds good. Well, we can maybe end there. I appreciate both of you. It sounds like in the future and folks, I think this is a very interesting topic in the sense that this is not a very cut and dry cookie cutter use case. It's a very sophisticated, very nuanced use case that reveals itself in the way we're doing our scoring, the fact that we have a human scoring going on, the fact that we have a fairly sophisticated training data set, and so on and so forth. And what we're finding is that newer models are giving us better results, and that's just setting the bar higher and higher for us. So as we kind of challenge ourselves to get to these improved performance expectations, I think we'll continue to share what we're learning with the rest of you guys in this community. So I appreciate everybody that's joining us on these discussions. And of course, you can always ask us questions on Discord, and we'll probably continue this conversation in maybe a couple of weeks. So I look forward to meeting you guys again. Thanks again for joining us.
Yeah, thank you for having us.
Absolutely. And to everybody who watched, have a great rest of your week, and we'll see you next week. Take care, guys. Thank you.